Welcome back to Unit 1, the diversity of matter and chemical bonding. Today we're going to be looking at chemical bonding, and we're going to start talking about electron dot diagrams. These are going to be tools that we can use to help us predict what kind of chemical bonding is going to occur between two atoms. And it's pages 14 through 17 in your Inquiry into Chemistry textbook. So by the end of today's lecture, you'll be able to describe how compounds are classified, describe using electron dot diagrams how electrons are arranged around the nucleus of an atom, and you will be able to describe how valence electrons are used to predict bonding ratios between atoms. So when it comes to classifying compounds, elements are rarely found in their pure elemental form. Most of the time, they exist in a compound where they have been, or where they are bonded to atoms of another type of element. And the type of bonding that it's going to occur between these two elements depends on the type of elements being bonded. And so it's really a matter of, are the elements metal elements or non-metal elements, or are they one of each? When we look at the metals, in nature they tend to combine to non-metal elements, so they form compounds that are called salts. And these compounds are always solid at standard temperature and pressures, or at 0 degrees Celsius and 101.325 kilopascals. This is just a set of conditions that compounds can be put at and compared. So when all these compounds are put at 0 degrees Celsius, when they're all under the exact same pressure, these compounds that contain a metal and a non-metal are always solid at this temperature and pressure. These compounds are called ionic compounds, and binary means two. So binary ionic compounds consist of one type of metal element bonded to one type of non-metal element, and some common examples include things like table salt, rust, and lye. So sodium chloride, iron oxide, and sodium hydroxide. Each of these compounds consists of a metal, which is the first name, sodium, iron, and again sodium here, bonded to a non-metal or a polyatomic ion. So chloride, oxide, and hydroxide. So these are all ionic compounds, binary ionic compounds. When we look at compounds that involve nonmetals, and only nonmetals, it turns out that compounds containing only nonmetals, they can be solids, liquids, or gases at STP. These compounds are called molecular compounds, and some examples are carbon dioxide, ammonia, alcohol, and hydrogen peroxide. One thing that chemists noticed very early on was that the noble gases, these nonmetals right in group 18, the far right-hand side of your periodic table, they never get involved in forming compounds. So in nature, they don't bond to other elements. So these are the group 18 gases, and they're inert. They don't get involved in chemical reactions. So chemists study these gases to figure out what made them so special. Why don't they want to react with other elements? And one of the clues came from looking at electron dot diagrams, which show only the valence electrons of an atom. So they use the atomic symbol of the atom to represent both the nucleus of the atom and all of those filled energy levels, because the inner energy levels don't participate in bonding. They are attracted to their own nucleus, and so they aren't attracted to the nucleus of another atom. Around the symbol, dots are placed, one for each valence electron in the atom. Now it's important to realize that electron dot diagrams don't show you what an atom looks like, and they don't show you how electrons are actually arranged around an atom. They're a tool. They're a tool that help us figure out how bonding occurs, but they aren't how atoms actually look. And we're only going to really worry about atoms and molecules that obey the octet rule, with the exception of hydrogen and helium. So the octet rule states that atoms try to get 8 electrons in their valence shell. Hydrogen and helium only get 2 electrons in their valence energy level, because they only have that first energy level. So 2 electrons at the most for hydrogen and helium. So for drawing electron dot diagrams, each atom has 4 available orbitals in each energy level. And each orbital can hold at most 2 electrons, so that's how you get your 8. 4 orbitals of 2, 4 times 2 is 8. If there are 1 to 4 valence electrons, then each one is placed in an empty orbital. If the atom has 5 to 8 valence electrons, then the electrons have to start pairing up. So they only pair up when they have to, because electrons are negatively charged, and so they try to space. They're repulsed by each other, or there's repulsion between them, so they try and space themselves out. So if they can go into empty orbitals, they will, but if not, then they have to go into an orbital that already has electrons. The paired electrons are called lone pairs, and they're not going to participate in chemical bonding. We need to see them because it lets us know that there's one spot on an atom that isn't going to get involved in bonding. The unpaired electrons participate in chemical bonding, and they're called, not surprisingly, bonding electrons. So here's an example of what some electron dot diagrams look like. Again, here's a sodium dot diagram. So you use the sodium symbol. This represents the nucleus. And the first 10 electrons are first 2 energy levels, because those don't participate in bonding. And so we only show the 1 valence electron. And remember, the number of valence electrons is equal to the number, or the group, the last digit of the group number. So for example, we know that phosphorus is in group 15, so it's going to have 5 electrons in its valence orbital. As we start pairing electrons up, so for example, silicon has 4 valence electrons, 1 in each orbital, and an orbital just exists on each side of the symbol. So there's 1 orbital, another orbital, 3 orbitals, there's the 4th orbital. So electrons space them out as much as possible, each one filling a spot. So even aluminum here has 4 orbitals. It has 3 orbitals that have 1 electron and 1 orbital that's empty. Once you fill all 4 orbitals, you have to start pairing them. And the order in which you pair them doesn't matter. This version of phosphorus and this version of phosphorus are exactly the same. Where you put that lone pair is completely arbitrary. Same thing, normally when you start filling up energy levels, you fill them up from starting at the top and then going clockwise around the atom. But if for some reason you wanted to draw your sulfur like this, that would be fine. As long as there's 6 electrons around that sulfur symbol, you've drawn an electron dot diagram for sulfur. So here we'll just draw some dot diagrams for some atoms, and we'll just go across the chart here. So for hydrogen, it's in group 1, which means it's going to have one valence electron, and its dot diagram would be this. Now it has 0 lone pairs and 1 bonding electron. So it has one spot that bonding can occur. There's a potential for bonding up here because we have an orbital that only has one electron. For magnesium, it's in group 2, which means it'll have 2 bonding electrons. So when we draw its diagram, it's going to look like this. It still has no lone pairs. It has no pairs of electrons that are together. It has 2 electrons that are in separate orbitals, so it has 2 bonding electrons, and so we have 2 spots for potential bonding. Carbon is in group 14, which means it has 4 valence electrons, and so there'll be 1 in each orbital. Still doesn't have any lone pairs, but it has 4 bonding electrons. Nitrogen is in group 15, which means it has 5 valence electrons. And now we put in our first 4, but we need 1 more, and so we can put that one anywhere we want. By convention, it's usually put at the top, and so now we have 1 lone pair of electrons and 3 bonding electrons. And for oxygen, it's in group 16, so it's going to have 6 valence electrons. And again, since we have more than 4, we're going to have some pairing occur. We can fill our 4, or we can put in our first 4 electrons and then start pairing up. So we're going to pair up twice. There's an oxygen dot diagram. It has 2 lone pairs and 2 bonding electrons. The lone pairs being the pairs of electrons in orbitals, and the other 2 lonely little electrons. That's where the terminology sometimes gets confusing even for me. These 2 single electrons are the bonding electrons. Neon is in group 18, so it has 8 electrons. And so it has full valence electron shell. It has 4 lone pairs and no bonding electrons. And this is why noble gases don't get involved in reactions, because it has no bonding electrons. It has no spots that are unhappy. It has a full valence shell. It has no need to get electrons from anywhere else. So there's nowhere around this atom where bonding can occur.